Hello everyone and welcome back to another little video on how to deal with parametric functions in Calculus 2. In this video, I'm going to be showing you how to get the arc length of a parametric function. And I'm going to start as usual by looking at the regular Cartesian coordinate functions y of x and derive the result from there like I did with the areas in a previous video. So again, assume the existence of some function here, y of x. And we want to find, again, its arc length from two x endpoints. This one, and maybe this one over here. We're trying to find the length of this segment. How do I do it? Well, one way is to break this curve, this interval, into very, very tiny straight lines, find the length of each one, and then sum them all together. If I can do that, you can imagine it being done like this. Again, this is exaggerated. Those blue lines are very, very small. They're basically infinitesimals called ds. Okay, so I'll fill the curve with ds's and I'll sum their lengths. But how do I find the length of one of these ds's right now? Well, if you notice for this one, for example, it seems like we have a little change here dy of its y component as we go from the top and slide to the bottom. We have a little bit of a change in its dx component right now. And the angle these two always make is 90. What do you know? I can actually use Pythagoras to get the length of this arc length element. And it will be nothing else than dx squared plus dy squared right now. So I can start from here, okay? And I can derive both the arc length formula for Cartesian coordinates and the arc length formula for parametric functions if I start from this. Let me do first, let me show you how it looks like if you try to do Cartesian coordinate arc length right now. You might find that handy. So how do you do it? Basically all you need to do depends on which variable you're going to be integrating. Right now, we are seeing here that we're going to be integrating with respect to x. So we want to have a dx at the front of our, integral. That means we need to factor here a dx squared, which will leave us inside a 1 plus dy over dx all squared. Okay. And then we can apply the square root on the little element here, leaving us with the square root of 1 plus the derivative of y with respect to x squared, and a dx sitting at the very front, and that is basically the length of our ds. Now, if we want to find, of course, the total length s of the curve that we've defined between x1 and x2, we got to do the integral. We got to sum all those ds's up. So we will integrate between x1 and x2 this quantity over here. And that is basically how we do it for Cartesians. We're not very interested about that though here in this video. We're showing it as a reference. We're interested in deriving the one for parametric equations. So to do that one, we want to make use of our implicit differentiation trick. Basically, I'm thinking that my x and y are both functions of t. And the only derivatives I can take right now really of those two guys is a derivative with respect to t. Wouldn't it be nice if my equation again worked here with derivatives with respect to t of x and y somehow? How can I make that happen? It would be really nice if I could do that. Because if I leave it like this right now, obviously this is not this, right? We've changed things and it's not the same thing anymore. I can bring, though, this later equation into the previous one by multiplying by something. And if you pay close attention, that something is dt squared right now. If I do that, I get rid of these, and I basically return to the upstairs form. So, I will keep these around. This is, again, how to use implicit differentiation, the little trick that we have, and express what's under the square root over here in terms of our parametrization. Right, so the next step here would be basically to factor the dt squared, leaving me with a derivative with respect of x with respect to t squared, plus a derivative of y with respect to t, also squared, under the square root. The square root here applies to my dt, leaving me with simply the derivative of x with respect to t squared, plus the derivative of y with respect to t squared, and my dt is sitting at the front. That is my length of the blue element there that we were analyzing previously. If I want to find the total here, I need again to integrate between some parameters t1 and t2. Okay, so how can I use that for my benefit now? Now that I have it in my hands, I can go around and find the arc length of any parametric function, really. So I have one lined up for you to test again as an example. Here it is. We want to determine the arc length of the following parametrically defined curve. And they've been kind enough with us to give us the interval for t. We don't have to dig it out ourselves. So we know we got to fill up right now this bad boy over here. And we have the bounds already set up for us, but we don't have the derivatives yet. The bounds are 0 to 1 from here. But what's going to go under the square root right now? Well, we have to take the derivatives, right? So the derivative of x with respect to t right now is simply going to be 6 times t. And the derivative of y with respect to t is simply going to be 6 but times t squared, as you can see over here as the 3 drops to a 2. Fair enough. So those are what we're going to place under these squares over here. So let's be really careful we don't miss a power here. So the derivative of x, 6t, and the derivative of y here, 6t squared. I'm going to go ahead and distribute in here the powers of 2. So I'm going to have, again, the same bounds, 0 to 1. And under the square root now I have 36t squared plus 36t to the 4th. I hope you can notice that we can actually factor the 36, but also a factor of t squared right now outside like this. So 36t squared can be factored, leaving me with 1 plus t squared for the second term here. Okay, now I can apply the square root to both 36 and t squared to get myself 6, which I'm going to pull completely out of the integral as it is a constant. And then this guy is going to become simply a t that's going to be multiplying the square root of 1 plus t squared. And this is the guy that we will be tasked to integrate right now. You might think this one is intimidating because, again, of the square root, but really a simple u sub right now will take care of this. All we have to do here is do a little u substitution for 1 plus t squared, because this guy's derivative, or at least part of it, is right here sitting on the outside. So we know u sub is going to be perfect for this scenario. We take the derivative of this with respect to t right now, we get simply 2t. So if we want to replace the t right now, the dt rather, we will have to do du over 2t. Now, while I'm at it, I'll also replace the bounds, so I do everything one shot with the integral. So if we have t going to 0, we plug 0 here, u is going to be going to 1. And if we have t going to 1, and we plug that into the substitution, we're basically going to have u going to 2. So the new integral that we have in our hands that we're dealing with is 6 going from, as you can see here, going from 1 to 2 in the u world. And now we have t square root of u, because that was what we basically defined as u. And then dt has been replaced with du over 2t. And like I promised, there's going to be some cancellation because the derivative of the inside of the square root was present on the outside, or at least part of it, off by a constant, that is. We have a little cancellation with a 6 here, giving us a 3. And all I have to integrate now is from 1 to 2. u to the 1/2 du. How I do that again? Basically, I'm going to move this power up by 1, so we're going to go to 3/2 if I do that. And to cancel, the effect that would happen, if I differentiated that right now, I would get a constant 3/2 coming down. So to cancel that constant, I have to multiply this by 2/3. So the derivative of this will exactly be right now u to the 1/2. Don't forget that we're evaluating this between 0, or rather 1 and 2. The 3's cancel. The 2 I can keep outside the evaluation of the endpoints. So we have right now 2 u to the 3/2. We start with 2 to the 3/2, and then minus, we see here 1 to the 3/2 as well. Okay, this is not going to simplify by much. So again, what I can try and do here, basically this can be, we can evaluate the cube portion first. So we're going to get 8 to the power of 1/2, or square root of 8. And then the other guy here is just 1. Any power that we raise 1 to is going to give us back 1. The root 8 can be simplified a little bit because we can think of it as 4 times 2. And if we distribute the square root in it right now, we can get essentially square root of 4 times square root of 2. Square root of 4 is just 2, right? So we are left with that square root of 2 inside. And so this gives us in total 4 root 2 minus 2 if we really go deep and distribute everything. So that is our arc length right now. It is going to be a positive number. We can tell right now size-wise. So we've done things correctly. It's a nice little check that we for sure haven't done a mistake. So again, very simple to find a formula for parametric equations if you start for how to find arc lengths and Cartesians and use a little bit of trickery from our implicit differentiation over here. Basically at this step, I am done. Once I've included that little trick, I just factor the dt outside and I have the formula for parametric equations, which I can use on whichever parametrization I have ever. So I hope that little example here, which is very characteristic, was helpful. I'm not making these too difficult because again, because of the square root, the functions that we tend to get under arc length evaluations are really nasty, pretty much terrible. So it's the results that are looking nice are very limited. And this is one of them, right? Cosines and sines can also give you cancellations to happen under the square root, but typically the integrals that we get for arc lengths are pretty nasty. This is one of the examples that plays nice. So this is how you do it. I hope this video you found helpful in how to actually find the arc length of parametric functions. If you did so, consider subscribing.